delay, and again, initial value in our system equals to 0, and after that we should take the second, which was used here, divided by 2, and then we will sum all poles or all time constants which we have here, and after that we will sum also all zeros if we have something here. So because we don't have, so we will use only those time constants. So it will be 14 and 10. So in that case, we will have 42, and our new first order plus dead time model will be the next. The same gain, then our time constant, and the delay is 42. So as you can see, we have one process, but we can describe it in different models. But for that case, just once, let's try to find out the second order plus dead time in order to understand how we should deal with that. So in that case, second order plus dead time, we should have, first of all, let's find the first time constant. It will be equal to the maximal one. So just it remains 120. Then we should find the second one. And the second one will be the next largest one, 36 plus half of the third one. So like that. So in that case it will be 43. And again, delay. So delay, we will have initial, which equals to 0. Then we should use the third one, which divided by 2. So 14 divided by 2, and all others, in our case, plus 10. So it will be 70. So the second order plus dead time model will be the next. 1 plus 120 plus 1 plus 43, our gain, and delay minus 17 is 43s. So this is simple case. Let's basically, because here we have negative sign, we just set that parameter, consider that parameter as a delay, and sum here. And this is all the difference. Maybe it's better to, because I don't have much time. Maybe it's better to use. Do I have? Yeah, it's better to use this example. So. Which one I would like to use? 1 plus 12s, and here I have 10 and 6s. And delay, yes. So here we have a problem. So if we have minus, then we can approximate it as delay. But here we have plus. And in that case, Skogerstat says that we can use such a rule. So first of all, we should check. If we have positive numerator, then we should find the neighboring denominator. What does it mean, neighboring? That, for example, our numerator 12, so the neighboring will be 10, not 6. So that means that values should be almost the same. If we can choose between many values, so we should consider a neighboring. So in that case, we should check for a rule. So what we have here, we consider those. Let's take another color. From our system, we select those, and let's rewrite. So, T P, that means denominator of all equals to 10. T Z equals to 12. Let's see. Our TZ is much more than TP. So in that case, we should consider our delay. Because our delay equals to 1, that means that we are dealing with this case. Yes? Because our 0 greater than our pole, and it's greater than our delay. So in that case, we rewrite this transfer as TZ divided by TP. So in that case, we divide 12 by 10 and we obtain 1.2. So basically, that means that right now we can consider this transfer as 13.7 multiplied by 1.2, 1 plus 6s, and the one delay. So this will be first order plus the time. This is the easiest case. I I have some examples in order, so when we multiply, you will obtain instead of that, you can write 16 like that. So let's consider more complex case. This is another example from my exercises.
I have a question.
Yes?
What is the criteria of neighboring? For example, if I have not 6 but 14, for example, which
Which is closest?
Yes.
Which is closest?
Yes.
Basically, that means that if the difference between two those, here we have difference 2, here we have difference 6, but if both directions we have the same difference, so basically it doesn't matter, because as you can see, for example, this is simplification, this is approximation of the model. We can describe the same process different way. As you can see at the previous case, at the beginning we had, so we described with pole which was 120 and delay was 60. But the same process we described as 136 and delay was a little bit smaller. So this is approximation. There is no perfect way how to, we simplify it anyway. So.
May I ask a question, please?
Yes.
As a remark to the previous one. I think we are doing what we are doing, that we are approximating the very complex process with the simplest differential equations. For example, the first kind differential, the first order differential equation. So that that process of approximation means that we are simply simply writing that function as a sum of simplest functions, and then some functions will be eliminated in the process because of their if they are small enough to be eliminated. For example, in this example, we can change 6 to, for example, 8. And then from, not 8, yes, as you said, 14, yes?
Yes.
And then if you have 2 approximations, then they would be close enough. But the one approximation would be upper one, and the other approximation with 10 would be down one. And then so your question is right about, it's very cool about approximation lines of the process, yes? If we choose one of them, then a process would be approximated by one of them, for example, the upper. And then the upper would be the upper, yes, I can't explain in English properly because it's like a boundaries, yes?
You are right, and from the mathematical point of view, because you have mathematical education, you are right. So basically, behind those processes, there is huge complex mathematical apparatus, but and we should consider it when we deal with complex processes and what we would like to obtain with our control. But from the practical point of view, basically, as I said, maybe in order to understand the behavior of the system, maybe it's just then you approximate such way you can see the difference if there is any by simulation. So okay, let's consider a little bit more complex exercise. This is the the more complex task. This is the last seventh then model. So here we have such a transfer function. We also have positive sign here. And delay equals to 3. So again, we are choosing the neighboring one. So in that case, it is one a little bit easier to choose. So what we have here? So 10s and 1 plus 12s. Our denominator parameter equals to 12. Our denominator equals to 10. But let's consider that case. Yes. What we have, our P much greater than TZ, but if we multiply our delay by 5, so in that case it will be 15, and in that case this is greater than others. So this is the last case, and for the last case, what should be done? First of all, we should find the TP tilde. In that case, we should write such way. So we take our initial parameter and then we take our 5-time greater delay, and minimal between those. Okay, this is approximation. Minimal between those will be 12. So our TP tilde equals to 12, and then we rewrite as you can see here, 12 divided by the real parameter 12, and then the pole will be T tilde, this is 12, minus TZ, which is 10 plus 1. So in that case, we will obtain 1, 2s plus 1. So we will have, so in that case, we can rewrite it like 1 plus 2s and 1 plus 23s, and like that. So and right now, in order to find out the first order plus dead time, so we will continue our Skogerstad method. So in that case, T10 will be equal maximal 1 plus half of the second one. It will be 24, and the delay, because of the previous rule here, and the delay for that will be 2 divided by 2 plus the original one delay will be 4. So finally, we will get such an equation. So our gain equals to 1, not k, just 1, and then our time constant is 24 plus 24s plus 1, or otherwise it doesn't matter how we write it. And e power 4, like that. Okay, in order not to confuse you, I will write it the classes over 24s, like that. So this is it. And again, why we use such a simplification? Because if you would like to tune PID controllers, mainly we will use first order plus dead time function. So this is it for today, and we will continue next week. Thank you for your attention.